Algebraic reasoning, chapter 1.6, exercises 1 through 12. This section of the book, 1.6, has to do with quadratic functions. We, thus far, in algebraic reasoning, have been working through linear functions and exponential functions, and now we go on to quadratic functions. For question 1 through 8, use finite differences in mental math as appropriate to determine if the data sets shown in the table below represent a linear, exponential, quadratic, or other type of function. In this set, I intend to do the odd numbered problems. 1, 3, 5, 7, 9, 11. And so the first thing we'll do is kind of look on the left side, and we make sure that we have these going up in increments of 1, and we can see that that indeed is the case. Now, what we're going to do is calculate what we call first differences. So we take 11 minus 5, it's going to be 6. 21 minus 11 is 10. 35 minus 21 is 14. And then finally, 53 minus 35 is 18. So we're going up plus 6, plus 10, plus 14, and plus 18. And so obviously this situation is neither linear nor exponential. And so what we do is we resort to second differences, but these are what are called our first differences. Okay, now to our second differences, we're going to take the difference between 6 and 10. So 10 minus 6 is 4. We went up 4. Then next from 10 to 14, that's going to be plus 4. And then from 18 to 14, that's plus 4. So these are called second differences. Okay, now it says determine if representation of okay. So since there is a common second difference, the function or the data set in the function, we'll say the function is quadratic. And you may have heard me say this before, is that where does the word quadratic come from? Well, the word quadratic comes from the Latin word quadratus, which means square in Latin. Next, let's go to problem number 3. Okay, we're going to go, okay, on the left side, we have our common differences on the left side is plus 1, and so on. Now the right side, we have 9 minus 5 is going to be plus 4. 16 minus 9 is plus 7. 29 minus 16 is plus 13. And 52 minus 29 is 23, is it? Let's make sure these are right. And 4, 7, 13. Okay. So our first difference is we say definitely not linear. Let's look at this. We say, okay, second difference are from 4 to 7. That's going to be plus 3. And then from 7 to 13, that's plus 6. And then from 23 to 13, that's going to be plus 10. Okay. So we got our first differences, our second differences. Okay. Our first differences and second differences are not the same. Therefore, not linear nor quadratic. Now it says exponential, so we can check for exponential. Let's do that one more time. I'm going to erase this. Just get a fresh thing here. So we should see, to get exponential, we'd have to have a common multiplier. So we take 9 divided by 5. What is that going to give us? And then 16 divided by 9. What is that going to give us? 29 divided by 16. And finally, 52 divided by 29. If these are not the same, which I don't think they are, we don't have exponential either. So 9 over 5 is going to simplify to 1.8. Okay, 16 point. The second one, let's get your calculator here. I didn't set this one up yet. Let me get this over here so we can see what it is. Okay, here we go. Documents. Slide. Screen. Okay. Now we're ready. Okay, 16 divided by 9. Oops. Put this below 9, enter. We'll go decimalize that. 1.77. So that's doesn't look the same. Next one we're going to do is take 29 divided, excuse me, 29 divided by 16. 29 divided by 16. What is that going to be? 1.81, so that doesn't look the same. Last one we're going to take is 52 divided by 29. That's going to be, oops, 1.79. So we're getting close. We had 1.75, 1.77. So 1.77. What are these other ones? 1.81, 1.79. So we say, I don't know if we could say exponential quad, but we could say very close to exponential. Okay, since we know our common ratio is, but we don't have an exact common ratio, right? 1.8. I don't know if we could say that it's exponential. We say an exponential model could be used, right? So I would just put it that way, that it isn't exactly the same, but we can use an exponential model. That's pretty close. Okay, next, 5. Okay, use finite differences and mental math. Again, we are going up +1 on the left side. On the right side, we're going up 12 minus 5 is going to be +7. 31 minus 12 is going to be, what is it, 19, is that right? 68 minus 31, that's going to be 37. And then 129 minus 68, that's going to be, is that 61? I think that is. So here are our first differences. Okay, so no, you would say no common difference, comma, not linear. Okay, now we're going to go to second differences. 19 minus 7 is going to be +12. 37 minus 19 is +12. And 61 minus 37, that doesn't look right, does it? Is that 61? No. Because 61 plus 60, yeah. $37, make sure that's right, 37. 61, no, it doesn't look right. Okay, 61 minus 37 is going to be +24. So second differences are not equal here, are they? So second differences not equal, not the same, therefore not quadratic. And we are certainly not going to have common ratios on this business. You know, do 12 over 5. Okay, is that the same as 31 over 12? Well, 12 over 5 is going to be 2.4. 31 over 12 31 over 12. Oops. Put this here. 2.58. Next, 68 over 31. What does that equal? Okay, decimal approximation, 2.19. And finally we have 129 over 68. So we find our decimal points 1.89 or about 1.9. So this really isn't close to a common ratio. So no common ratio, or really not even close, right? So not exponential. So that really is our answer, right? Not linear, not quadratic, not exponential. That is our answer, number 5. Next, number 7. Okay, same mission here. Use finite differences in mental math. On the left, we know we're going up 1 every time. On the right, 11 minus 5 is going to be 6. 24 minus 11 is 13. 53 minus 24 is plus 19. And 117 minus 53 is it's going to be 464. So we don't have, so our this first differences are not equal. 13 minus 6 plus 7. 19 minus 13 is plus 6. 64 minus 19 is 45. It's 45. Okay, so not quadratic either. So not linear, not linear. And second differences are not equal. Okay, not quadratic. And then finally, exponential. Do we have 11 over 5 for a common ratio? Do we see that? 24 over 11. What is that? 53 over 24. Now they look like they're going to be a little over 2, all of those. This one's going to be 2.2. This one here is going to be a little over 2.2. And the last one we have is 117 over 53. Let's try these other ones here. We got 24 over 11. Okay, we get 2.2 about. Okay, that's about right. 2.18, that's about right. 53 over 24, I think that's going to be close. 53 over 24, boom. Okay, that's going to be 2.2. Very close. 117 over 53, I think we're going to see that. Oops. 117 over 53. So that's going to be 2.2. So very close, 2.21. So this one here is, we'd say, an exponential function how do we say that? Closely models the data. So we would say it like this. Probably, I got in this video a couple more problems to work out. So just 9 and 11. Questions 9 through 11. The data sets shown in the tables represent quadratic functions. Use finite differences to determine values A, B, and C. Well, first the rules are, okay, for quadratic, the y-intercept is the point 0, C. And so for this one right here, we have x equals 0, y equals 7. So C is equal to 7. Okay, the next rule is second difference, put the rules over here, is equal to 2a. So our first difference here is plus 3 plus 9, and 34 minus 15 minus 19 is plus 15. And then our second difference is going to be 9 minus 3 is plus 6, and plus 6. So our second difference is 2a, so we can just say 6 equals 2a. So if we divide by 2, a is equal to 3. So a is equal to 3. And finally, y values for x equals 0. And, or between, the difference between x equals 0 and x equals 1. If we take the difference between those two, we would have a plus b. So let's look at this. We have the y values where x equals 1 and x equals 0. So that's going to be 10 minus 7 is going to be 3. So we could say a plus b is equal to 3. Well, we already know that a is equal to 3, so 3 plus b is equal to 3. Subtract out 3, so b is equal to 0. So I put b is equal to 0, and write the function in standard form. Well, the function in standard form is going to be f of x equals ax squared plus bx plus c. Well, in this case, f of x is equal to ax squared, and a is 3, so we get 3x squared, and b is 0, so we do not have an x term, plus c, which is 7. So this is going to be our answer here for problem number 9. Okay, the last one we're going to have in this set is, and this video lesson is going to be number 11. So same process. We notice on the left we're going up by 1. On the right, we have 5 minus negative 1 is plus 6. 19 minus 5 is going to be plus 14. And then 41 minus 19 is going to be plus 22. So those are our first differences. We go to our second differences. We have 14 minus 6 going to be plus 8. And then 22 minus 14 is plus 8. And then we have the point 0, comma c, right, is going to be our y-intercept. So our c is going to be equal to negative 1. And then we have the second difference equals 2a. So 8 is equal to 2a. Divide by 2. And we have 8 divided by 2 is 4. So a is equal to 4. So I'm going to put a equals 4. And now the differences between these first two terms, 5 and negative 1. So we're going to have 5 minus negative 1 is going to be equal to a plus b. And so 6 is equal to a plus b. And so we already know that a is 4. So replacing a with 4, 6 equals 4 plus b. Well, if we subtract 4, we have b is equal to 2. So we have b is equal to 2. So in standard form, our function here is going to be f of x equals ax squared. So that's going to be 4x squared plus bx. So it's going to be plus 2x plus c, and c is minus 1, negative 1. So that's going to be our quadratic function in standard form. And then go ahead and work all these odd number problems out. You'll be in great shape. Good luck, and thanks for viewing.